Okay, this is going to be the video for section 2.6 in differential equations on numerical methods of solution. And we're specifically going to talk about one numerical method called Euler's method. Um, Reminder that when we are studying differential equations, if we have a first order differential equation, which is what we're doing all here in chapters 1 and 2, you could always solve this differential equation for the derivative, dy dx equals some function of x and y over here. And when we first started imagining what this would look like in the chapter 1 part, we said, therefore, if you plug in xy for any xy here in the domain, then you're going to get a value which is equal to the derivative at that xy point in the plane, right? Which represents the slope, and we can make something called a slope field, right? Where we plot those with little infinitesimal sections here like this. And when we find the solution to a differential equation, we're finding y as a function of x of some kind. And then there's many solutions, usually solution families. But if we have an initial condition, then we have a particular point where we have to know what y is at an x. And so we can establish the integration constant to figure that out. And that produces a particular solution, which is one curve in the xy plane here that will follow all the slopes, so that if you plug in the xy's anywhere along here, you're going to end up getting the derivative of this, so the slopes will match the form in the original differential equation. Okay, that graph produces a solution curve for any particular initial condition. All right. So, we now know a lot of ways to find that solution curve analytically. Okay, all different methods that we've learned throughout chapter 2. But not all differential equations are going to be in forms that we know how to solve. In chapter 4, which we're actually going to do next, we're going to talk about another set of methods that we can use when we have higher order derivatives. So we have second derivatives or third derivatives in the differential equation. But even then, we'll be left at the end of the course with some differential equations we won't have a method to solve. Right. So, but a lot of times we still want to know something about the solution curve. We need to use that to analyze some problem. So whenever we can't find an analytical solution to a differential equation, we can resort to a numerical method to find an approximate solution. So we can come up with a solution curve where the y's are the approximately correct values for the given x's. Okay, and there are many such methods. And typically we use computer programs to do these things, because there's iterative calculations at every x point to find the matching y. And in fact, if we have time in this class, we will, at the end of the course, teach you some MATLAB programming so that you can use a piece of software to compute these things. But it's good to know how they work underneath the hood. And so we're going to look at one particular method called Euler's method. Now, this method is not typically used when we do software because it's not super accurate and it takes a long time to converge to good solutions. But it's it's the simplest method, and it's a good way to illustrate the general idea of how these methods work. Okay, so this particular method, Euler's method, takes advantage of the fact that when you have a differential equation, first order differential equation, where you can put everything on the right-hand side except for the dy dx over here, then that means the right-hand side represents the slope at some particular xy point. And as long as you have an initial condition where when you know some x0 value, you can plug it in and find, or what the y value is, which then defines a specific solution, then that means that at this point, we know one point that's on the curve. And by plugging it into the differential equation, we know one slope value. So we start out knowing one point on the curve and the slope in the immediate vicinity of that point. Okay, so Euler's method takes advantage of that and says, all right, so here's where I start. I start at some initial point, x0, and I know what y0 is, and I know the slope here because I can get this from plugging into the differential equation. Maybe I'd like to know what y is at some other desired x value. Maybe it happens to be above that point, let's say. So I'm really trying to figure out, what is this point up here? What's the y for this desired x? So what we do is we say, all right, let's take that distance between where we are now and x and divide it into some little iterative steps. like maybe a step, and we're going to call the step size h. So we're going to move a distance of h from wherever we are at our initial condition towards the x where we want to be to solve a point. And then we're going to say, what if I were to add that h to the initial condition x? So now I'm at x plus h. Then there's going to be another position here, and we'll denote this point x1. So we'll call this position x1, and its matching y will be y1. Okay. Now, because this tangent line of the slope is tangent to the curve, this point will be approximately in the right place as the actual solution. Not exactly, but pretty close, a numerical approximation of that. And because we know that the slope is equal to change in y over change in x, then that derivative dy dx, which is equal to the right-hand side, it's whatever we get in when we plug in our initial value into the right-hand side of the differential equation's f function. That slope has to equal change in y over change in x, but change in y is y1 minus y0 over the step size h. And then we can solve this for the new y value. Y1 is therefore equal to the old y value updated by adding the step size times the value of the slope at the previous point. And then this is iterative. So we use that point then as a jumping off point to do this over again. We go another step size h to come to x1 plus h, which we call x2. We plug this value in to the derivative equation to find the slope at the last estimated point on the solution curve to get that slope. And then we say, okay, y2 is therefore equal to y1 plus the step size times the dy dx evaluated at the x1 point. And that gives us another little jump. And so this point is approximately equal to the true solution value. Now, we just keep that up until we finally get to our desired x value, and then whatever the result is, we just keep going here. Whatever the result is the estimated y. That's the approximate y for the actual y on the solution curve. And actually, I'm exaggerating this, but usually the error here is usually very, very, very small. If you take small enough steps, right? This is the issue. If you try to jump too quickly, then you're going to land pretty far away. But if you're willing to go with many, like if we were willing to go with 10 steps here instead of 3, we would the slopes would remain very close to the line at every point, right? So you can trade off granularity, like time to converge to the solution, with how close you want to be, right? But in a computer program, of course, you could just standardize this and say, okay, we're going to do 1,000 steps every time. And you'll have a very, very good solution. It'll just take a long time to run, is all. Okay? Because here's the deal, right? You would have to start out with a point like that, and then use that to compute points in the vicinity, and then use those points to compute points in the vicinity around that, and sort of slowly fill in the points around here for the whole XY plane to find that, right? So that could be very time consuming if you're trying to generate an entire slope field this way. Okay. All right, so this is called Euler's method, and in the homework tonight, we're just going to have you practice this by hand for a couple of cases, and we'll just keep our step size at 0.1, but let me show you an example of what this would look like. So let's say I have this differential equation. Now, I could solve this differential equation because this is separable. I could solve this, right? I could move this to 1 over y over here, right? Well, actually, this would be linear. Yeah, I believe I could convert this to a linear form and then solve using one of our methods. Right, but let's say we're going to do it with approximation. So I know that dy dx, or y prime, is equal to 0.2 xy, and I have the initial condition that when x is 1, y is 1. So that's a known point on the solution. I would like to get an approximate solution for what y is when x is 1.5. Okay, and let's use a step size h of 0.1, which means to go from 1 to 1.5, we're going to have to take 5 steps. We're going to go from 1 to 1.1 to 1.2 to 1.3 to 1.4 to 1.5. And when we get to 1.5, the y here is the approximate value. So at each stage, what we're doing is saying that the next one, n plus 1, is equal to y of n plus the step size times the dy dx evaluated at the nth point. Okay, so for example, when I start at the 0.11, the next y will be the y from the previous point plus the step size times this, which is you just plug in this 0.11 into the right-hand side of the derivative of the differential equation because that gives you the derivative. And so that computes to 1.01. So now we're at the point 1.1 in x and 1.02 in y. And then we use this as a starting point. So now this 1.02 becomes the new starting y plus the step size times the derivative, but we evaluate the derivative with this x and y. And you just keep doing that iteratively until finally you get to the value that lands on your desired point, and that means that the final y here is equal to the approximate y on the solution curve at that point. So what we've been able to do is say, okay, I know that this point at x is 1, y is 1, and I wanted to know what this point is at 1.5, let's say, okay? So I've just found out that this is approximately 1.1258, right? And that's going to be very close to the correct value for the solution curve. That's really all it is. It's just an iterative procedure. We just want you to practice a little bit so you can kind of see how it goes, so that when we do get to the MATLAB part of the course, you'll understand kind of what's going on under the hood. It's going to be stuff like this, right? Now, Euler's method, it takes many iterations to come up with an accurate solution, and therefore it doesn't converge very quickly to good accuracy. So there are other methods that are used. Probably the most common one is called the Runge-Kutta method. It's named after two German mathematicians. And we'll explore that a little bit further when we get to the very end of the course and we revisit numerical methods here. We're actually going to learn the MATLAB programming language, just enough to be able to program in a differential equation so that we can have it produce a solution curve so that we can answer questions. And we're actually going to use a program called Octave, which is an open source program, which means it's free. You can download it for pretty much any platform, Mac, PC, Linux, Windows, whatever. And it uses the same syntax at MATLAB, which is a purchase program. So how we actually do it will depend on what mode we're in terms of instruction modes when we're in class. We may have actual MATLAB installed if we're doing this on computers at school. If we're still at home in some way, we might need to have you install this free program if you're willing to. I know we'll talk about that when we get closer to the end of the class, but we'll at least show you so that you have notes on how to use a free program called Octave to come up with numerical methods and solutions. All right, and then in the notes, I have one last thing that I added in, which lists all the methods we have to solve first-order differential equations, right? So the first thing we ask ourselves, you can kind of think of as a big tree, is are the variables separable? Can you separate all the x's on one side and the y's on the other side? If you are able to, then you just integrate both sides. Okay, if you aren't, then you should ask the question, can this be written as a first-order linear equation, right? Which means dy dx plus some function of x only p y equals f of x. If you can write that, then you can multiply, you can use the px to find an integrating factor, and the specifics for that are listed back here. So you use an integrating factor and then integrate both sides, okay? Now, if it's not separable and it's not first order linear, then you can try to separate the dx and dy to see whether or not it happens to be a first order exact form, which means you split the dx dy. If you can write it as a function m dx plus n dy and dm dy happens to be equal to dn dx, then you can use the exact procedure. This is the one, I also put the steps here at the back of the notes, where you're doing something that's kind of like finding a potential function in Calc 3. And then the solution is that potential function equals an integration constant. So first separable, then first order linear, then first order exact. Okay, if it doesn't match any of those forms, then we can ask, is it a Bernoulli form? Is it in the form of a linear equation except, oh, there's a typo there, there should be plus. Is it in the form of a linear equation except that the right-hand side is a function of x times y to a power? And if that's true, then we can do a substitution u equals 1 minus n, which will convert it to a form that will usually become first-order linear, so we can use first-order linear forms. If it's not Bernoulli, is it a composite function, which means there's an inside function and an outside function? If so, you can try substituting the inside function as u. and that will convert it usually into separable form. If it's none of those, then we have to resort to a numerical approximation method, at least right now. Okay, and that's pretty much it for this section. So just give the homework a try and try to see by hand what's going on when you do these linear approximation methods.